All right, so we have 13 to the x minus 14 to the x all over x as x goes to 0. And you're supposed to use L'Hopital's. First thing before is just make sure that it qualifies. So when you plug in 0, you get 13 to the 0 minus 14 to the 0, which is 1 minus 1, which is 0. And on the bottom, you just get 0. So it is an indeterminate form. So it's okay to use L'Hopital. Okay. So then it's just a matter of taking derivatives. So we differentiate top and bottom separately. And this one, you just have to memorize the derivative form. It's 13 to the x times natural log 13 minus 14 to the x natural log 14. That's an automatic. There's no, the chain rule is just 1, so it doesn't really affect anything. And then you take the limit of that again. So far, so good?
Yes, it was the next part because on the get help for the example problem, when they simplified it,
Okay.
the it just became natural log 13 minus natural log 14. And I wasn't sure how they got to that step.
Oh, we just plug in the 0. So 13 to the 0 will give you 1. 14 to the 0 will give you 1. And then all that's left over is these two guys. You get ln
Oh,
13 minus ln 14 all over 1, which is just this.
okay.
In fact, if you want, you can combine that as a quotient, a single natural logarithm.
Okay. Yeah. See, I'm tired and I thought they did some sort of fancy simplification and I forgot a rule, but they just plugged in 0. Okay. Thank you. That helps a
Well, that
lot.
should always be step number 1 on any limit. Just try the number out. Sometimes it works.
Okay. All right. Thank you. Thank you. I was just staring at it. I wasn't sure what I wasn't doing.
All right, no problem. Well, glad we cleared that up.
Yes.
Do you have other questions?
And I wasn't
Uh,
sure
I'm going to
how
share it.
relevant. Okay.
Um, hold on. So we have this derivative question, match the functions with their derivatives. Which one was you? I'll bet you, was it number 1 you were wondering about? That's one
No,
that one's
so
come up.
um I eventually got them all. It's just two of them weren't straightforward simplification. Two of them I had to kind of manipulate with
Okay.
identities to kind of get the answer that they had. Let me go back.
You know what?
Yeah,
This
I
is a
was,
good, let me write these down because this is actually a good question to review some trig. And I think the questions are mostly the same for everybody on this one.
yeah, it was just, okay, here, I'm almost there.
All right. I'm gonna go to my overhead
Okay.
and then I'll come back to this screen and see what we get. On the first one, you can do that as a product rule. See, this is a case where you got two options here. You can actually trade out tangent for sine over cosine, and that would give you sine squared over cosine. And then you just do the quotient property on that. The bottom derivative top minus top derivative bottom. Derivative bottom is going to be minus sine, so it's going to be plus sine cubed x all over the bottom squared, which is cos squared x. And if you distribute here, well, you get cosine squared x. And frankly, that's simplified. Or you can just take it the way it's written, do the product rule on it. So you do first derivative second plus second derivative first. And both of these are the same thing, believe it or not.
Yeah.
Um, the thing with this particular problem is they give you like a list of choices, and if yours don't match up to what they've offered you, you have to somehow fiddle around with it to try to make it match using identities. In reality, if you were just working this out as part of the problem, any of these answers would be acceptable. And my habit has been personally to just do everything in terms of sine and cosine. Very rarely do I work with the other ones. I work with tangent sometimes because it's an easy derivative, secant squared. But other than that, I pretty much ignore like cotangent, cosecant because I just don't remember anything about them. I just convert them back into sine and cosine equivalents. So these are both acceptable as answers. Now the answer list may make you uh, toy around with it until you find an equivalent form. And there's other cases like right here, the derivative, there's really not much you can do about this one. It's the same one. It's going to be negative sine of the inside. So sine of tan x, then times the inside derivative, which is secant squared x. And that's pretty much simplified. That one's not going to be simplified any much more. Now I'm going to show you
Yeah,
one. Go ahead.
oh, I was gonna say, yeah, for that one, they just wanted it instead of the secant squared of x, they wanted it the cosine squared of x on the bottom. So that one was really simple.
Yeah.
Um,
I think what they're trying to do is they're trying to throw some curveballs at you. You get an
yeah,
answer, and then it doesn't match any in the list, and then you have to think, wait a minute, there's probably some identities going on here. This is one's actually come up a few times. I take the 3 down, and I get cos squared x, and then I do the inside here, and I get um, negative sine x is the derivative. And if I wanted to make it look a little prettier, I can move the negative outside of the 3. And that's a good answer right there. I mean, this is perfectly fine. I think on this one, I think they screw around with it. I think they actually take like a sine over cosine and a cosine cubed to make it tangent. Is that what they did? I'm going to go to my overhead real quick.
yeah, they multiplied both. Oh, I figured it out.
Yeah, it's this
They
one
like
right
added a cosine to each one or something.
right here. It's D, and so I'll write it down. Now I got to be honest with you. I would never ever in a million years do that. There's no reason to make it more complicated. All right, so I'm going to go back to my page here, and that's what they did. They actually multiplied the top and bottom by a cosine. That ups this guy to a cube. Now you have one on the bottom. Suddenly the sine of a cosine makes tangent. And these are all the same thing. Okay. Um, it's a funny problem. I guess they're trying to make sure that you understand some identities. On this one, this is just secant squared, and that's it. Okay. So never would I do that. All right, this is actually a preferred answer. It's in sines and cosines and it's reduced. In fact, it's even stupid. I'm going to go so far as to say it's silly to do this. You want to know why?
Why?
Well, because what's the domain of this function?
Sine 3 of x. Well, that's just all real numbers,
All
right?
real numbers, yeah. Uh-oh, we got a denominator.
Oh,
Suddenly, tangent has restricted domain, doesn't it? It's not true for odd pi halves. So suddenly, for some crazy reason, we've introduced a tangent into this, thereby restricting the domain. In fact, now that I think about this, I don't like this problem. I'm gonna
okay.
write.
That makes me feel better. I thought the problem was ridiculous.
I may actually bring this up with the people who pose this question because I think it's actually technically it's not quite right because it restricts the domain unnecessarily. There's no reason to restrict the domain. that's kind of, we don't want to do that. We don't want to make things more complicated. All
Yeah.
right, well, anyway, I guess it's a good practice to remember your trig identities. That's about it.
Okay. Yeah, I wasn't sure if there was some special reason they had us do it. To me, it just seemed more complicated than the most simplified answer there was. So
Yeah,
I wasn't sure if you had any insight.
no, I don't. I'm actually gonna
Okay.
make a screen capture of this and give me a second here. I'm gonna just do this for my own. All right, so I've got that for my own. Got a student here. All right. Uh, where were we? Okay, so does that help you with that one?
Yeah, that like I said, I just was like, how practical is this actually? So I thought I
Well,
was missing something.
no, you're not missing anything. It's other than just
Okay.
to force you to practice some of your trig identities. That's about the only pedagogical reason you want to do that.
Okay.
Okay, but from a mathematical, from like a common sense, there's no reason to introduce something that has restricted domain. So this is not quite the correct derivative here. I'll write this all the same up to domain. So there's some domain issues that enter into play here. Yeah, I'll be bringing this up with the text. I think that's not a good question. Sorry about that. Sometimes
No,
these
no.
things get past me. I don't even pay attention. It's like, looks like a good question when I looked at it, and then now that we've talked about it, I'm not so sure I like the question.
I mean, it was good practice for the derivatives of trig functions, but then past that, it was a little excessive. I
Yeah, well, I agree with you there.
think,
Um, this one, right?
yes. I think I just had a small mistake that made me redo it like 5 times.
Yeah,
But
this
is
one's
it
come up a few times. I think we also, it's addressed in the ed discussions too. Um, this is number 7 on 2.6. And you want to find the equation of the tangent to the curve at 3, -1.
and I think when I started it, now I think I just made a small mistake and that's what made this really hard for me. But at first I tried to have I had the 2 over 25 on one side, and then I brought the other stuff to the other side. Is that valid? Can I do that?
Let's work it out. I can't tell just by saying that. I'm going to do the derivative. So
Okay.
on the left side, it's going to be 4x squared plus y squared. That'll be the first power. And then the chain rule kicks in. Every time I take the derivative of y, I got to put a dy dx. And on the right side, I'll distribute 25 through. So 2 comes down, you get 50x, and then minus 50y dy dx. And what I would do in a case like this, since all we need is a number, is I just go ahead and plug in the values. So you plug in 3, -1. Let me just go ahead and show you the step. So let's clean that up. That's going to be 9 plus 1 is 10, 40. That's 6. So we have 46 and -2. So we have 240. Take away 80 dy dx. On the right side, we have 150 plus 50 dy dx. And if I move this -80 to the right side, that becomes 80 plus 50 is 130 dy dx. And if I subtract the 150 to the left side, it becomes 90 So then dy dx is just 90 over 130, which is 9/13. And that's the slope. Now I'm not, so does that look like what you did?
I couldn't even tell you. I'm trying to remember what was my issue, and I think it was a small mistake. And I tried to simplify. I thought I was simplifying at first by dividing both sides by 25 and then moving the x squared plus y squared to the other side. And then I ended up having to do like the quotient rule
Yeah,
derivative. And I made it messier. And I
yes.
think that's what was giving me issues.
I mean, that would work, but you have to be very careful doing that.
Yeah, it gets very long, and
Yep.
I kept making a small mistake and it would just like throw off the entire thing. So,
Well, you never want to use the quotient unless you don't have a choice.
okay.
Okay. I'm just showing the remaining steps. You just use the point slope formula for the equation of a line. That should be acceptable. If not, distribute out the, see, -27/13. This will be -13/13. So another equivalent answer would be 9/13 x, and that'd be -40/13, and of course y equals. Okay. Yeah, don't use the quotient property unless you have no other choice. In fact, that's a good hint for the mastery test coming up. Just because it's written in quotient form doesn't mean you have to use the quotient property. You should always look to see if it's simplifiable, and maybe you get lucky. Maybe you can get some factors that cancel, and you don't have to use the quotient property. And you certainly don't want to rewrite it so that you have to use the quotient property. What you said will work, but as you have discovered, it gets really ugly really fast. And there's no point to make life difficult that way. We're trying to make life easy for you guys. We're all about easy at ASU. We don't want to work very hard. Just joking. Does that help?
Yeah, thank you. Like I don't know why I
So 3.5, number 3, it's the tangent of the sine inverse of x. Okay, so this is kind of a question I think a lot of people trip up on, because this arc sine business gets a little weird. And there was a couple questions that were on ed discussions where I could tell people were struggling with it. This is actually an angle. It's the angle. So sine inverse of x is actually an angle um, whose sine is x. And I'm going to write it as a quotient because that's using that SOHCAHTOA, the right angle, right triangle. And so I'm going to write it right here like this. So the sine of this angle, I'll put a little theta in here to represent the angle. Its sine is opposite over hypotenuse. So far, so good? Because that's what sine is, right? Opposite over hypotenuse. And then by the Pythagorean theorem, you've got to actually get the third side. So I'll put a little note here. Use the Pythagorean theorem to get this adjacent ADJ side. And so I'll call it lowercase a for now. So I know that according to the Pythagorean theorem, I square the legs and I add them, and I get 1 squared to hypotenuse, which is just 1. So if I solve for a, I get square root 1 minus x squared, and that's what that third side is. So I'll put a little circle around it. Now that's not the answer to the question yet, but that gets us real close to it. So I'll stop you for just a moment, and let me ask you, does that make sense what I just did? Anybody can jump in at any time and ask for clarification. Okay. So remember, inverse tangent, inverse sine, inverse cosine, anytime you see that -1, it means arc or inverse, whatever. It's an angle. This whole expression is an angle. And you're just simply trying to decompose it using right triangles. Now, here's the thing. The beauty of this is that you've got all the information you need to answer the question. So now we come down and we say the tangent of whatever this angle is, the tangent of the inverse sine of x, well, tangent is opposite over adjacent, right? So you can see that out of the shadow. And so the opposite, looking at the triangle, is x, and the adjacent is √1 minus x squared. And that is your answer.
That helped to phrase the arc sine x as it being an angle. I didn't think of it that way, but
well, and it's a good way to. It's the so think about it. When you take the sine, if you write sine x equals something, x is the angle, right? Sine x. But if you write sine inverse x, you're actually swapping the meanings. It's think about the unit circle. It's really just a coordinate on the unit circle. So here you're just swapping the inputs with the outputs. This little skill here is going to be super critical in Calc 2 because you're going to be doing a lot of trigonometric substitution integrals, which are a lot of fun and takes up like 3 whole pages just to do one problem. And a lot of times what you have to do is you have to convert back into the original variable, and you have to use this little method here. So you're going to be drawing right triangles all day, but it's a good skill to know. So just a little warning for you guys. If you take Calc 2, you're going to see a lot of this weird tan of sine inverse stuff and sine of cos inverse and that kind of thing. And then you get to Calc 3 and we completely turn it around and we do a spherical integration. And that way we don't have to mess with the trigonometric substitution. So a lot of good stuff ahead for you guys. On this one, this is 8x times arc sine x, which is the same as sine inverse x. So the derivative is just going to be an application of the product rule.
Mm-hmm.
So I just write out my parentheses and I go first, which is 8x, derivative second, and that's one you just have to memorize. Okay, now if you want the proof of that, I can do it for you. Plus the second, which is arc sine, times derivative first, which is 8. And it doesn't really clean up much then. I can bring these together as a single fraction. I can move the 8 out in front. And that's about as pretty as it's going to get.
Mm-hmm. Okay.
And there's no backwards conversions that you need here. Does that address what you were looking at?
Sorry, say that again.
Does that address your question?
Yeah, that may have not been the best problem to ask you on. I was just trying to think of something where we can walk through.
I can make one up.
Yeah, that'd be great.
How about the sine of the cos inverse of x? Now, I'm not going to do the derivative. I'm just going to do the right as an algebraic expression. Is that okay? Is that what you're looking at?
Yeah.
Okay, so this is a good time let's look at this thing, big picture. Cos inverse is the same as arc cos. So ARC is kind of the word you can use also. It's the angle whose cosine is, and again, I'm going to use the fraction form, x over 1, because I'm thinking cosine, I'm thinking adjacent over hypotenuse. So I'll use theta as my temporary angle measure. And this time I want x over 1 because again, actually I made a mistake. My bad. That. It's adjacent over hypotenuse. I was thinking tangent. Sorry about that. So I put my x and my 1 where they should go. So adjacent over hypotenuse. Then I use the Pythagorean theorem to get the other side. It's actually going to be the same as what I had on the previous problem. So net square root of 1 minus x squared. And then I say to myself, all right, now I'm ready to find the sine of that. Sine of theta, which is, remember, theta is the angle that we're wondering about. Well, I just kind of read it off. It's going to be opposite over hypotenuse. It could be radical 1 minus x squared all over 1, but you don't have to write that. In fact, if I wanted to do tangent of cos inverse, well, I've got all the information here. It's going to be opposite over adjacent. And I'm done. That makes sense?
Mm-hmm.
And so hopefully seeing that helps you incrementally move forward in terms of understanding how the inverse cosine, inverse sine, all that stuff behaves. And if so, that's good. You know,
Mm-hmm.
that big Lego structure, you're building it one block at a time. All right. Any last questions from the audience? Kaylin, Laura, Griffin, throw another one at me, try to confuse the professor. No. All righty. Any last comments?